Okay, this is exercise 4C from the Cambridge worksheets. This is question 11. It says a car moves along a straight road from its front gate, where it is initially stationary. So that we know that if we take x equals 0 as the front gate, we know that at time 0 that the velocity is 0. It says that during the first 10 seconds, so from t equals 0 to t equals 10, we've got a constant acceleration of 2 meters per second. And then it says for the next 30 seconds, so from t equals 10 seconds to t equals 40 seconds, the acceleration is 0. And then for the next 20 seconds, so from t equals 40 seconds to t equals 60 seconds, the acceleration is -1 meters per second because it says it decelerates at 1 meter per second. Now, before doing part A, I'd like to do part B. I want to sketch the graphs of acceleration, velocity and distance from the gate. So I'm going to start with the part B actually first. So the acceleration curve. So we know that we go for 60 seconds. So 10, 20, 30, 40, 50, 60 seconds. We know that in the first 10 seconds there's a certain acceleration, and that's a constant acceleration of 2 meters per second. So I'm going to make this the acceleration axis. This is my time axis in seconds. But we have a constant acceleration for the first 10. I'll just write seconds. We know that it's in seconds. Constant acceleration of 2 meters per second for the first 10 seconds. And then from time is 10 seconds to 40 seconds, so 10, 20, 30, 40, we have a 0 acceleration. So we can't have a coloured in dot there and there. So we know it's definitely for the first 10 seconds. Then after that, so I've got an open circle here for the next 30 seconds. So up to and including the 40th second, we have 0 acceleration. And then from time is 40 to 60 seconds, we've got an acceleration of -1. So open circle there at 40 and closed circle there at 60. Okay, now that's our acceleration graph. Okay, now we know that velocity as I was saying, that we know that the velocity, so just up here, we know that the velocity is the integral of acceleration. So we'll put our time scale down the bottom, 10, 20, 30, 40, 50, and 60. We know that when time is 0, velocity is 0. And again, when time is 0, velocity is 0. And we know that for the first 10 seconds, that acceleration is a constant 2 meters per second. So velocity is the integral of acceleration with respect to time. So in the first 10 seconds, velocity is the integral of 2 dt, which is 2t plus c. We know that when v equals 0, t equals 0, and so therefore we know that v equals 2t, so that gives us c is 0. Now when time is 10, so when t is 10, velocity is 2 times 10, which is 20 meters per second. So therefore, sorry, that's coming off screen a bit. I'll just fix that. So therefore, when time is 10 seconds, velocity is 20. I'll put that this is 20 up here. Now, there was another way of doing that. We know that velocity is the integral of acceleration. In other words, it's actually the area under the acceleration curve. Now, this velocity is the integral of 2, is really only the velocity curve from 0 to 10 seconds, okay? So if I actually want to work out the maximum velocity there, then I can see that it occurs when t is 10 seconds, because when I substitute t is 10, I get 2 times 10 is 20. But just notice about that. So when t is 10, v is 20. Now we know from t equals 10 seconds to t equals 40 seconds that the acceleration is 0. It doesn't mean that it's not moving, it just means that you've got constant velocity. So therefore from t equals 20 to t equals 10 seconds to 40 seconds, we've got no acceleration, in other words constant velocity, and we know that we're already travelling at 20 meters per second, so therefore up until 40 seconds we've got a constant velocity of 20 meters per second. Now from time equals 40 to time equals 60, we've got an acceleration of -1 meter per second. Now I'm going to do a similar thing here, but of course we've got a different, we'll be integrating something different this time. So we know that so that was just for time equals 0 to 10, but velocity is integral of acceleration, which is the integral of -1 dt, and that will be the velocity curve for t equals 40 through to 60 seconds. So therefore it's -1 t plus c. Here, there's going to be something happening here. I know that when time is, now I can't use when t is 0, v is 0, because that's for that line there. But I do know that this point is the beginning of whatever I'm going to draw here. And I know that when time is 40, velocity is 20. So when t is 40, velocity is 20. So therefore I get 20 is -1 times 40, which is -40 plus c. So therefore c is 60. And so therefore velocity is -1 t, or -t plus 60. Now, I'm just going to, I know I've got this point here. So my final point will be when t equals 60 seconds, my velocity, I just put it into that equation, is -60 plus 60, which is 0 meters per second. So therefore, at 60 seconds, my velocity is 0. Okay, so I come back there. Okay, now notice that the particle stops at time equals 60. Okay, so, and we know it's decelerating, so it's getting slow, it's going slower. So it's slowing down. See here it's speeding up. Here it's at 20 meters per second, but here it might be traveling at, I don't know, here say 10 meters per second. Here it's traveling at 20 meters per second, because this is velocity. Then it traveled at a constant acceleration, sorry, 0 acceleration. In other words, constant speed or velocity for those 30 seconds. And then it decelerated, so it started going slow, and we can see that here it's at 20 meters per second, here it's traveling at 10 meters per second, and here it's stopped. Okay, so the particle has stopped there. All right, now I have to draw the displacement curve. So we have to draw the displacement curve and show where the particle is. Now we know that initially at time is 0, we'll just draw our times again. We know that when time is 0, x is 0. Now, we also know that to find x, it's the integral of the velocity curve with respect to time. Now, I can work out the equation of this line, integrate, and if I, so I've got a certain line here, so I would integrate between the values of 10 and 0. But instead of doing that, when you do integrate, you're actually finding the area beneath the curve. Now, it's much easier to find the area beneath that curve by doing the area of the triangle. So therefore, the distance travelled from time equals 0 to 10 seconds will just be the area here under this curve. So I'll just have to make this a bit, pull it out a bit. So from t equals 0 to t equals 10, the displacement or the distance travelled, actually just distance travelled, is a half times the base times the height. So it's a half times b times h in that triangle, which is a half times 10 times 20, which is 100 metres. So therefore, in the first 10 seconds, we travel 100 metres. I'm going to make that 100 metres. Then in those next 40 seconds, so coming up here, in the next 30 seconds, sorry, I can integrate this, and that will give me the area under the curve. But integrating velocity, remember, gives me displacement or distance travelled. So therefore, if I find the area of this rectangle, which is 30 times 20, that gives me the distance travelled from, so the first one was t equals 0 to 10. So if I want t equals 10 seconds to 40 seconds, the distance travelled is 30 times 20, because it's a rectangle, which is 600 metres. So if that's 100, I've got 2, 3, 4. Actually, I might change this scale. I don't know if I'm going to fit everything. 1, 2, 3, 4, 5, 6. So 600 metres over the next, sorry, actually, I am going to have to change this scale. One sec. So it travels an additional 600, which should take me up to 700. So actually, I'm going to change this a bit. I'm going to make this 100 down here, like about halfway there. And then we go an additional 600, which takes me up to 700. So this is 2, 4, 6, 800, 600, 400, 200. So I'm up to the 700 mark after the 40 seconds. Now, okay, I'm going to do this again. So I'm going to go, let's go 300 there. So that would be 200, 400, 600, 800. We're going up to 1,000, 1,200. So, okay, I'm going to draw this again because the shape's actually not right. If you think of this, remember, to get displacement, you have to integrate the velocity. Okay, now we do have the displacement curve. We know for the first section, we've got velocity equals 2t. And if you integrate that, you will get 2t squared on 2, which is t squared. In other words, you've got like the shape of a concave up parabola. So we do know that at time 10 seconds, we've travelled 100 metres. But how do we get there? It's not with a straight line. It's a concave up parabola shape. So that's got to be a concave up parabola. The other thing that gives away that this is a concave up parabola is that from time equals 0 to 10 seconds, the acceleration is 2 meters per second, which is positive. Acceleration is greater than 0, positive, which means that remember we've got, when we look at our curves, we've got displacement, velocity, acceleration, and the acceleration is the second derivative, which is actually the concavity of the original curve. So if the acceleration there is positive, the curve is concave up, okay? So the area of this bit is 100. The area in this section here we worked out was 600. So therefore we've travelled up to 700. So we've got 600, 800. So there's 700. Now, this is a straight line. This section here we've got constant, zero acceleration. Therefore we've got constant velocity. And if you, for example, this, the equation of this line would be v is 20. And if you integrate that, you get 20t, which is a straight line. So I've got concave up there. I've got straight line there. Sorry, it's just not very clear. So I'll try it again. I've got concave up here. I've got straight line there. Oh, it's still not very clear. I really need a bigger scale here. Okay. I just haven't really left myself enough room. So concave up there, curved. Straight line there. Now we know here the acceleration is negative because we were told in the question from time equals 40 seconds to 60 seconds, the acceleration was negative. So this will be a concave down curve. Now we need to find this, if we integrate under the velocity curve there, we get the distance travelled again. So coming back down here, so from t equals 40 seconds to 60 seconds, the distance is going to be the area of the triangle, which is a half of, now this is 20 and that's 20. So it's a half of 20 times 20, which is a half of 400, which is 200 meters. And so therefore the total distance is 100 plus 600 plus 200, which is 900 meters. So we end up in the end at 900 meters, and that happens after 60 seconds, and this curve is downwards. It goes like that, concave down. And you want concave up, straight line, concave down. Okay, so that is the displacement graph. Okay, and that's in meters. Okay. All right, so if you want distance travelled, so to find distance travelled, you need the area under the velocity curve. Okay, because if you integrate velocity, whenever you integrate a function with respect to, say, the x-axis, you're finding the area beneath, enclosed between the x-axis and the function. Okay, so that gives you distance travelled. Okay, now going back to part A, the maximum speed. If you just look at your graph, the maximum speed is 20 meters per second. Okay, so back to part A, your maximum speed is 20 meters per second. Sorry, just looking at that down here. Maximum speed is 20 meters per second. And how far does the car go altogether? Well, altogether, car travels, oh, I've got it down there. So the car travels 900 meters altogether. Okay, now for question 12. I think that one's okay. So, yeah, that one's pretty okay, fairly straightforward. All right, I'm going to look at question 14. Okay, we've got this graph here. It says this graph shows the particle's velocity versus time. We can see we've got negative velocity here, zero velocity there. Looks like maximum velocity there and zero velocity there. So this is question 14. It says, when is the particle moving forwards? Now it'll be moving forwards when its velocity, so moving forwards is when velocity is positive, greater than zero. Now positive velocities occur, that's between t equals 4 through to t equals 14 seconds. Okay, that's when the particle is moving forwards. And of course we can write that as time. It has to actually, it's between 4 and 14. It doesn't include 4 and 14 because at t equals 4 the velocity is 0, and at t equals 14 velocity is 0 as well. So it's times greater than 4 but less than 14 seconds. Okay, that was part A. Part B is, when is the acceleration positive? Now remember, acceleration is dv dt, so it's the derivative of the velocity graph. So therefore it will be when the gradient of the velocity is positive, and here we've got a positive gradient of the velocity. So therefore acceleration is greater than 0 when or between, so greater than time is 0. This looks like it could be the gradient here could equal 0, so it's for time greater than 0 up to time less than 10 seconds. Okay, so it's between 0 and 10 seconds. Okay, now when is the particle furthest from its starting point? Now we can see here that we've got negative velocity because you'd have negative values here. And then we've got positive velocity. So here the particle's moving to the left, okay, because the values of velocity are negative. But here the values of velocity, if we look at this axis here, these values of velocity are positive. These values of velocity, even though they're getting smaller, so this just means that the particle's moving faster along here, okay? So it's moving faster in the positive direction, and this is the maximum velocity up here, but this particle's still moving in the positive direction because the values of velocity here are still positive, and the value of velocity here is still positive as well. So in other words, for all this section, the velocity is positive and it's moving furthest from its starting point. Okay, so the furthest it would be, so from 4 seconds to 10 seconds, the particle is moving to the right. Okay, so away from the starting point, and so therefore it would be furthest from its starting point at t equals 14. So we've got at t equals 14, it's furthest away from starting point, and that's because from t equals 4 to t equals 14, we've got a positive, we have positive velocity, therefore it's moving to the right. Okay, we do have some negative velocity for the first 4 seconds, so it's moving to the left, but then it's moving back to the right again. So once we've passed, let's say, this amount of time, which will counteract those 4 seconds there, we're just moving further and further away from the origin, so it's moving to the right at that time. Now it is moving, the particle does move to the left, or in the negative direction, from t equals 0 to t equals 4 only, okay, and the gradient doesn't seem very different, or that area, sorry, in here. See, the area here, the other thing you've got to remember is displacement or distance is the integral of velocity. Now this area here between 14 and 4 is a lot bigger than the area from 4 to 0. So the other thing is that you'll be at a position further away from the origin at time equals 14 because you've got a bigger displacement under here compared to this displacement here in the negative direction under there, okay? So, and the area we can say from t equals 4 to 14 seconds is larger than the area from t equals 0 to t equals 4 seconds, which, you know, is in the negative. This is negative velocity here, but this is positive velocity here, moving to the right. So it's moving more to the right than this little bit here to the left, okay? Now, question D says, when is it furthest in the negative direction? Now, at time is 0, it does have negative velocity. It's moving in the negative direction. And it's still moving in the negative direction here, where my cursor is, and it's still moving in the negative direction. And when it gets to 4 seconds, it stops because the velocity is 0. And then it starts moving with positive velocity. So it moves in the negative direction for the first 4 seconds. So therefore, it'll be furthest in the negative direction at time equals 4 seconds. Furthest in the negative direction at t equals 4 seconds. Okay? Because at t equals 4 seconds, it stops and heads in the positive direction after that, and heads in the positive direction from t equals 4 to 14 seconds, okay? So it's at t equals 4. Now the next question says, about when does it return to its starting point? So we've travelled, so remember, starting point is asking you about position. So they're asking about displacement, okay? So displacement's got to do with area underneath the velocity curve. So this is negative velocity, so the area will be the absolute value of this. So looking at this area, if I cut the graph off about here, and I'm thinking that might be at about, I don't know, 8, I'm not sure if it's 8 or 7 seconds, somewhere between 7 and 8 seconds. I just want to get this area here equal to an area above here. Thinking somewhere about there. Look, we could say that it's about 7.5 to 8 seconds or something. So it's it returns, when does it return to its starting point? It returns to starting point at approximately 7.5 to 8 seconds in time. And that's where we want the area from t equals 0 to t equals 4 is approximately equal to the area, absolute value, sorry. So the absolute value of the area from t equals 0 to t equals 4 is approximately equal to the area from t equals 4 to about t equals 7.5/8 seconds. All right. Now, the thing is, this distance here is in the negative direction, and this distance here is in the positive direction. So the particle would, the negative would balance out then with the positive, taking you back to its starting point. Because remember, it starts here, traveling to the left, but then traveling back to the right, okay? And around there it would end up at its starting point. Starting point does not necessarily have to be the origin in this case, all right? Now, on part F, it says to sketch the graphs of acceleration and displacement. Oh, now it is saying assuming that the particle is originally at the origin. The reason we didn't know before is that because when you integrate velocity, you'll get the displacement curve plus c, and we didn't know what the constant was going to be. But they're saying that the particle is originally at the origin, and we have to sketch the graphs of acceleration and displacement. Okay, now for part F, I'm just going to draw, the original curve, and that's the x curve, sort of looks like this. 14, that's 10, this is 4, that's obviously 0, this is velocity, and that's time. Now the acceleration curve, remember we've got x, v, and a. Acceleration is the derivative of this. Now it looks like we've got 0 gradient there and 0 gradient at 10. So for acceleration, we've got 0 acceleration at 0 seconds. And we've got 0 acceleration at 10 seconds. Remember, acceleration is dv dt, which is the gradient of the velocity curve. So we're saying here gradients positive, positive, positive. Then we've got gradient 0, then we've got negative gradient. Okay, so we need to say that we've got, that's a small positive gradient, then it's quite big. I'd say the maximum velocity is around here somewhere, and then maximum acceleration is there, the maximum gradient, the steepest, is there, and then it will come back down to 0. So it looks something like this. And then here we've got negative gradient of velocity, which means negative acceleration. And it goes something like that, okay? So that's your acceleration curve. Okay, and then the displacement curve. Now, we need to look at the information that we gathered in the question, okay? So we know that it said at time equals 14. If we just go back and look at what we did, we know that we've got, what's it asking? It's moving forward for the first 10 from time equals 4 to 14 seconds, and it's also moving backwards. It's moving backwards from time equals 0 to 4 seconds because the velocity there is negative. So Just looking back at what we had. It did say that it starts at the origin, and we'll do our times here, 4 seconds, 10, that was about 8, there was something happening there, and about 14. Okay, and we said it'd be furthest from the origin at 14. We said that in the first 4 seconds, we can see that the velocity is negative, so it's moving away from the origin. But then here the velocity is positive, and we said at about, I think, at about 7.5, 8 seconds that it would come back to its starting point, okay? And then we've got, and then it keeps traveling, and at time 10 seconds, it's still positive velocity, but it's slowing down, okay? So you'd get it to start tapering off after that, okay? And also here, look at your acceleration. You've got positive acceleration, which means concave up to 10 seconds, and then negative acceleration, which should mean concave down for your curve from 10 to 14 seconds, all right? So you need to show that concave up, concave down for 10 to 14 seconds. So that's your sketch of displacement versus time, okay? That's really, really important, all right? You really need to look at your acceleration to get the shape of your original curve correct as well. Okay, acceleration positive up to 10 seconds, concave up. Acceleration negative from 10 to 14 seconds, concave down from 10 to 14 seconds as well. Okay.